law states that the total momentum of an isolated system remains constant. For that, you need to understand what is meant by an isolated system. An isolated system is a system which has no net external force, which means it may have an external force, but there won't be any resultant external force. So if there's an external force, then it would be balanced and the resultant would be equal to 0. So the first thing is that the total momentum of an isolated system remains constant. Isolated system is the one which has no net external force. Then what is meant by external force? External force is the force applied by a body which is not considered part of the system. So when you would apply law of conservation of momentum, you could apply it to one particle or two particles or three particles. They would be considered system. An isolated system is the one that has no net external force. So a system would be a system of one particle, one body, two bodies, three bodies, whatever you consider a system. And so any body which is not part of the system is going to be called external. And any body which is not part of the system, if that exerts force on the particles of the system, then that particular force is going to be called external force. So if there is any external force, means force being applied by a body which is not considered part of the system, then it won't be an isolated system. So if a system is isolated, that is, it does not have any net external force, then the total momentum should remain constant. Okay, although you understand it, but I would want to repeat it once again, that wherever I'm going to apply law of conservation of momentum, it would be either one particle or two particles or three particles. They would be called system. And anything that exerts force, which is not considered part of the system, is going to be called external force. So there may be an external force acting, but that external force should be balanced. So when an external force is balanced, then there is no net resultant force. And when external force is being balanced, then we say that the system is isolated. And for such system, the total momentum should remain constant. I'll try and explain that way. It's a little tricky concept, and I'll try and explain that way with the help of certain examples. Let's talk of one example in which a particle is moving on a smooth horizontal surface. So a particle is moving on a smooth horizontal surface. So if I try, and there is no air resistance as well, I'm going to consider air resistance to be negligible in all of these examples. So there's no air resistance. Particle is moving on a smooth horizontal surface. Then it would be acted upon by two forces. One is the normal reaction, and the other one is the weight. The system over here is just this particle. And if the system is just this particle, then the normal reaction is exerted by the table, which is not part of the system. So normal reaction is an external force exerted by table. Just like that, gravitational force is exerted on this particle by Earth. So Earth is also not considered part of the system, and the force exerted by Earth is also an external force. Despite the fact that I have two external forces acting over here, I would still say that it is an isolated system. Reason being the fact that we know that these two forces are equal and opposite. So I said isolated system is the one which has no net external force. So even if there are external forces, but the resultant is 0, so I'd still say that there's no net external force. And if there's no net external force, then it will be an isolated system. And if it is an isolated system, the momentum should be conserved. Momentum is mass into velocity. So if you'd also notice, guys, this is just a restating of Newton's first law. In Newton's first law, you said that an object moving with constant velocity with no resultant force would continue to move with the same constant velocity. You're saying the same thing, but slightly differently. You're saying it's an isolated system and its momentum would be conserved. So if you might notice, you're saying the same thing in two different ways. In Newton's first law, you said no resultant force, it will keep on moving with the constant velocity. Over here, you're saying that there's no net external force, and hence the momentum would be conserved. So you would say this example is more of a restating of Newton's first law, which is why, I mean, when we talk about conservation of momentum, we have to have a very strong foundation of the laws of Newton, because we use them to understand the conservation of momentum. And now, we're going to talk about another example where I have an example of two particles moving on a smooth horizontal table. The table is smooth and horizontal, and there are two particles moving, and M1 is moving faster as compared to M2, so that it can reach up to M2, it makes a collision, and they will exert force onto each other, and they'll move off again, with, of course, V2 being higher, and M2 will be moving at a higher speed, so that it moves away. So this is an example. Now, the first thing I want you to understand is that if I just consider M1 as a system, so from this situation before collision to at collision to after collision, I cannot say that it is an isolated system. Because although at this point of time, it has still normal reaction and weight acting on it, they are balanced and there's no net external force. But when it has a collision with the particle M2, and since I'm not considering M2 as part of the system, so there is a net external force acting on it. And if there's a net external force acting on it, so its momentum would not be conserved. So I would say momentum of M1 here is not equal to momentum of M1 over here, because M1 was not an isolated system. The reason M1 is not an isolated system is because when M1 collides with M2, which is not being considered part of the system, then M2 exerts a force onto this. And because of that, there's a net external force acting on M1, and hence its momentum is not going to be conserved. So I can't apply law of conservation of momentum on M1 alone. Now, but what if I consider both M1 and M2 together as part of the system? Because the problem was that M2 exerted a force on M1, and M2 was not considered part of the system, which is why I couldn't say that the momentum of M1 is conserved. But how about taking M1 and M2 as system? A system could be of one particle, a system could be of two particles, a system could be of three particles, and so on and so forth. So how about considering M1 and M2 as a system together? So if I consider M1 and M2 as a system together, then when an impact occurs, M1 experiences a force, fine, but that force is exerted by M2, which is part of the system. Or M2 experiences a force, but that's exerted by M1, which is still part of the system. So despite that the individual momenta of M1 and M2 would not have been conserved, but if I consider M1 and M2 together, then their total momenta must have been conserved, because before collision, at collision, after collision, there is no net external force, because these two forces have now become an internal force, because they're exerted by something which is now considered part of the system. So I would be able to say that momentum is conserved. So individual momentum of M1 and M2 is not conserved, but the total momentum of M1 and M2 together are conserved. So what's the total momentum of m1 and m2 before collision? m1u1 plus m2u2. What is the total momentum of both particles after collision? m1v1 plus m2v2. So total momentum of m1 and m2 before collision is equal to total momentum of m1 and m2 after collision. And hence you get a formula which you use a lot, which is m1u1 for collision of two bodies, which is m1u1 plus m2u2 is equal to m1v1 plus m2v2. So what we're trying to say over here is that, well, there are two particles which are about to collide. So we have a picture before collision and we have a picture after collision. This still is a smooth, flat, horizontal surface. But when the collision occurred, they exerted forces onto each other. So if I consider both the particles together, then that would be an isolated system because there would be two internal forces acted upon each other. So what is the momentum? Let me name them. Let's say I say that one particle is A and the other particle is B. So what's the momentum of A before collision? That's 5 into 2. That's 10 Newton second. What is the momentum of B before collision? That's minus 12 Newton second. What is the momentum of A after collision? This is still 2 kg. That is minus 6 Newton second. So, I mean, I can clearly see that momentum of A is not conserved because it was not an isolated system. It experienced a force by B, which was not part of the system. But if I consider A and B together, then I know that A's momentum would not be conserved, B's momentum would not be conserved, but their total momentum would be conserved together. So if you could see, what's the total momentum here? Minus 2. So what should be the total momentum here? That should still be minus 2. So if total momentum has to be minus 2, so I can figure out that B's momentum after collision has to be 4 Newton seconds, so that the total momentum has to be conserved. And if it is 4 Newton seconds, and if I know its mass, then I can find the velocity. That would be 4 upon 3. Well, I broke this down into steps for you to understand it. But somehow you can directly use a formula which is m1u1 plus m2u2 is equal to m1v1 plus m2v2. So you could say 2 times 5 minus 3 times 4 equals minus 2 times 3 plus 3 times v. And you will solve this equation and you would be able to calculate the velocity, the final velocity after collision of particle B. Okay, guys, so this is more of a mathematical proof of conservation of momentum. So you still apply the same concept, but somehow if you could see the final result is same, but this is how you mathematically prove it by using Newton's second law and third law together. So you know, I mean, they're moving with constant velocity, still they interact with each other. But at the point of impact, they exert equal and opposite forces onto each other. So you would say that F1 must be equal to minus F2 because they're in the opposite direction. How do I get it? Newton's third law. And then if you look at individual force, if you look at individual particle that experiences a force, and according to Newton's second law, that force must be equal to rate of change of its momentum. So if it's initially moving with velocity u1 and finally moving with velocity v1, then for particle m1, the rate of change of momentum would be m1 v1 minus u1 over t. That's the time of collision. And for particle 2, its initial velocity is u2 and final velocity is v2. The change of momentum would be m2 v2 minus u2 over t. That's how we define Newton's second law. It's the rate of change of momentum. Okay. Of course, the time for which m1 experiences a force is equal to the time for which m2 experiences a force. So these are equal to times. You can cancel them off, multiply them, simplify them, and you will get the law of conservation of momentum being proved. But if an object falls under gravity, and I assume that there's no factor of air resistance over here, then this particle falling down cannot be considered an isolated system. It can't be considered an isolated system because it experiences weight exerted by Earth. So if it experiences weight exerted by Earth, so its individual momentum would not be conserved. So as a particle falls down under gravity, the momentum of this particle is not going to be conserved because it is not an isolated system. The reason it is not an isolated system is because it experiences weight, which is exerted by Earth, which is not considered part of the system. If you would consider the Earth and the falling particle together, then they now would be an isolated system. What I've done is that I've made my system bigger, and by considering system as particle and Earth together, so I would say that particle experiences weight by Earth. So if I pull Earth as part of the system, then weight is no more an external force. And that means that as the particle falls down, despite the fact that only particles' momentum would not be conserved, but particles and Earth's momentum would be conserved. So the change in momentum of particle downwards must be equal to change in momentum of the Earth upwards. And you may say that, sir, why don't we see Earth moving up? Because momentum is mass into velocity. So with such a huge mass, the change in velocity of the Earth is very negligible.